Okay, in the last file we discussed about the derivation of Darcy equation, then we discussed about the derivation of Chase's formula, then we had a brief understanding of the minor losses, at least the expressions. Now in this file we will discuss how to solve numericals on Darcy equation, Chase equation, minor losses and combined major and minor losses. So directly I'm going to page number 6 where I have solved few examples. Apart from these examples, you can also go through some of the solved examples in the textbook. So understand the logic behind the expression, how to critically analyze the equation, then any problem can be solved. So in the first problem here, pipe diameter is given as 50 centimeter, length of pipe is 1 kilometer or 1000 meter, discharge is given as 200 lps, coefficient of friction for material of pipe is given as 0.001, and you are supposed to find the loss of it due to friction, that is HF. So it's a straightforward equation where HF is equal to 4FLV square by 2GD. F is value of FLD are given, but only thing is velocity is indirectly given. But we know from continuity equation that V is equal to Q by A. So Q is 200 lps, that is 0.2 meter cube per second, divided by area of pipe gives you velocity as 1.01 meters per second. Please verify these values once again using calculator. Therefore HF is equal to 4FLV square by 2GD. Make sure all the parameters are in SI units, so we get the loss as 0.423 meter. A very simple example where most of the values are known, one unknown, one equation, you can always solve that. Now in the second problem, discharge is given as 250 lps, length of the pipe is 5 km, diameter is 50 centimeter, loss of head due to friction is to be found out. So here it is written as V is equal to Q by A. Since discharge is given, area of the pipe is known, in the sense diameter, you can easily find velocity, but F is not given. So compared to the previous problem, here F is not given. But since we know the density of fluid, viscosity of the fluid, first find the Reynolds number as rho Vd by mu. So if you substitute the value of rho Vd by mu, you'll get Reynolds number as 636,619. Obviously it is more than 4000, so it's a turbulent flow. So the formula to find F is 0.079 by Ru to the power 1 by 4. So you got the value as 0.00279. If Reynolds number is less than 2000, you have to use 16 divided by Re as F. So once the value of F is known, again the problem becomes straightforward one. One equation, one unknown. Substitute the value of 4FLV square by 2GD. You will get the loss as 9.24 meter. Sometimes we make a common mistake of not squaring velocity. So please be careful about using this equation. This is the second problem where F is also unknown, HF is also unknown. Now the third problem, here formula remains same, but the problem is defined in a different format. So I'll just go through the problem statement. In these files I have written only the data given. So there is a city of population 2 lakh. The water requirement per person per day is 15 liters. The length of flow between the city and the reservoir is 6 km. It is observed that the loss of head between the reservoir and city is 24 meters. We are supposed to design the diameter of the pipe. In the sense, we have to calculate what should be the minimum diameter of the pipe. So it is given that coefficient of friction is 0.001 for a material of pipe. You can see the F value is given, and one condition is given that half of the daily requirement has to be pumped within 8 hours. This is a condition, maybe the condition for the pumping of water. So pump capacity is such that half of this daily requirement will be pumped in 8 hours. Let's see. So if you see in this problem, if I use HF is equal to 4FLV square by 2GD, HF is given, F is given, L is given, D is unknown, and V is also unknown. Where velocity is Q by A, Q has to be found out. Area of pipe again includes diameter. So except V and D, remaining three parameters are known. Now coming to the velocity. Velocity is known as or defined as discharge by area. So we don't know the discharge itself. So to calculate discharge, again I need the volume of water and the time required. So first you have to calculate what is the volume of water required per day for that city. So 2 lakh people into 15 liters divided by 1000 is to convert into meter cube. We get that 3000 meter cube of water is required. Now it is given that half of this has to be pumped in 8 hours. So as Q is volume by time, so if you multiply 3000 meter cube into half divided by the time taken to pump that water, 8 into 60 into 60, we get something called as 0.05208 meter cube per second. And please remember, this is nothing but the rate of flow of water, because discharge is volume by time, volume is 3000 meter cube, but half of this, that is 1500 liters a meter cube, has to be pumped in 8 hours. So indirectly the data is given, you have to use that in calculating Q. And once Q is known, you can find velocity as Q by A. Q Q is 0.5208 meter cube divided by area of pipe where diameter is unknown. So you get velocity as some value divided by d square. Now if you use the Darcy equation, HF is equal to 4FLV square by 2GD, you can see that d is unknown, v is also in terms of d. So it is one equation, one unknown. If you substitute all the values, you will get the value of diameter as 18.6 centimeter, somewhere close to 6 inches. Now one care has to be taken is velocity is squared and velocity is 0.0663 by d square. So when you square that, it becomes d raised to 4. 1d is already there in the denominator, so totally it becomes d raised to 5. So here please make sure that you don't make any calculator mistakes. So diameter of pipe required to supply the water to the city from a reservoir of 6 km distance is around 18 centimeters. This is one problem. In the next problem, the same problem is solved by using Chase's formula. Before that, one more example is given where Chase's constant is given. Length of pipe is around 2 kilometers. Loss of it is already known as 18 meters. Diameter of pipe is given. You have to find velocity. So here V is equal to C root Mi, where M is hydraulic mean depth, D by 4, I is HF by L. So it's calculated. D is already given. So if we substitute V is equal to C, which is also given as 50, into root of M and I, all values on the right hand side are known, you will get the velocity of flow as 1.18 meters per second, just to make you understand the terms involved in the Chase's formula. Next, another example, there is a hostel having a strength of 2000 students. Then length of flow, that is water is supplied to that hostel from a reservoir which is 5 km away, and it is observed that head loss is 18 meters, and Chase's constant for material of pipe is given as 45. Again you have to design the pipe, in the sense you have to find the diameter of the pipe, but it is given that water required per person is again 15 liters. He says that half of this requirement of water for the hostel has to be pumped within 6 hours. You can take it either as a condition or compulsion. The pump capacity is half the water requirement will be supplied in 6 hours. Now again, first we'll calculate the volume of water required, number of students into water required per student, divide by 1000 to convert liter into meter cube. It is calculated that 30 meter cube of water is required per day. All these calculations are per day. Now half of this has to be supplied in 6 hours. So 30 into half divided by 6 hours, convert that to seconds, gives you 0.00069 meter cube per second. This is the discharge. Now this discharge divided by area where d is unknown gives you velocity in terms of a constant divided by d square. So earlier we solved the same problem using Darcy equation. Here we will solve it using Chase's equation. So Chase's equation is given by V is equal to C root Mi. C is 50, root of M and I. M is again d by 4 where d is unknown. Squaring, you will get a number on the left hand side. 45 will be squared and square root will go there, and finally you will get d raised to 5 is equal to something, and I need not have to explain much about the simplification part. So once you know all the values, substitute and get the diameter of pipe. So diameter here comes close to 5.3 centimeters, so which is quite reasonable, right? So this is another problem where data is given in the indirect form. So next we'll look into some problems on minor losses. Here you can see a problem is given where pipe suddenly expands from diameter d1 to d2, and we are supposed to find pressure in the larger pipe given the pressure in the smaller pipe. Both diameters are given and discharge is also given as 200 liters per second. So here we need not have to worry about which equation we use. All these problems on dynamics can be solved by Bernoulli's equation. So when I apply Bernoulli's equation, it is E1 is equal to E2 plus losses. In E1 part, substitute P1 V1 square by 2G Z1 and all that. But losses here, it is appropriate to consider the minor loss due to expansion. So I have written the formula V1 minus V2 square by 2G. So if you calculate V1, it is Q by area of first pipe. So V1 can be calculated, V2 is known. So when you substitute everything, you can see that except P2, all the other values are known. So you'll get P2 by rho G as 21.1 meters. So P2 is around 2.07 bar. So similar to these problems, there are many worked out examples in all the textbooks, mainly R.K. Bansal and K.L. Kumar. I request all of you to go through that. Now at the end, a problem on combined major and minor loss is solved. You can see that a pipe is connected at one end to a tank. The other end of pipe is open to atmosphere. The diameter of pipe for first 15 meters is 10 centimeter. Then for remaining 20 meter length, the diameter is around 20 centimeter. That is, pipe expands from 10 centimeter to 20 centimeter. Total length of the pipe is 35 meters. And the height of water in the tank is around 4 meters. We are supposed to calculate the velocity of flow through the pipe. So here we have marked pipe 1 and pipe 2 as shown, and we have to apply, or we have to solve this problem by considering both major and minor losses. And again, the only solution, or the solution is possible by using the Bernoulli's equation. But the question is where to apply the Bernoulli's equation. For that reason, 2 points are chosen. So to avoid confusion between again 1 and 2, I have chosen the point as A and B. So applying Bernoulli's equation at point A and B, we get EA is equal to EB plus losses. So EA is again PA, VA square by 2G and ZA and all that. Similarly EB plus losses. But in these losses, you have to count all the losses. So first, fluid enters into a pipe. So loss of head due to entrance, head loss due to friction in pipe number 1, HF1, sudden expansion between 1 and 2, HE, plus loss of head due to friction in pipe number 2, that is HF2. So when you expand, the equation is as shown. But if you see, both point A and B are open to atmosphere, so pressure there is 0 and fluid is not moving at point A. So pressure at A is 0, velocity at A is 0, ZA is 4 meters considering center of pipe as the reference. Then at point B, pressure is 0, VB is what we are supposed to find out, ZB is 0 because reference line passes through point B. Next, these losses are now expanded, and one thing we can make sure that V2 and VB are same because both are at the same point. So finally we get 4 is equal to HI is V2 square by 2G plus V1 square by 2G, 4 F1 L1 V1 square by 2G plus V1 minus V2 whole square by 2G plus 4 F2 L2 V2 square by 2G D2. Now if coefficient of friction is same for both material, same material of pipe, if both pipes are same, then F1 and F2 are same. But here you can see that there are two unknowns, V1 and V2. Now using continuity equation, you can convert one velocity in terms of other. So if I use A1 V1 is equal to A2 V2, as the pipe diameter is doubled, the velocity is reduced by 4 times. So V2 is V1 by 4 or V1 is equal to 4 V2. So if you substitute this continuity equation parameter in the above equation, the equation turns out to be the equation of single unknown, and one equation, one unknown you can always calculate. So once the velocity is known, you can calculate the discharge. So apart from this problem, exactly similar to this, along with a single pipe or one more tank attached to the other end of the pipe, there are 4 or 5 worked out examples in R.K. Bansal textbook. I expect all the students to go through the same. So this concludes the second video, which is flow through pipes related to the numericals.